So we're looking at still the flow over the plate. So we've got the U infinity, P infinity flowing over this rigid plate. There's no slip condition on the plate. We've got the viscous boundary layer building up above the plate. Still trying to get a size for this viscous boundary layer. We had the X momentum equation, which told us these were the scales. The inertial forces were the X momentum equation, were scale U infinity squared over L. Pressure forces P over L rho. And viscous force, the dominant viscous force, was nu times U infinity over delta squared. Now I'm going to take a look at the y momentum equation. So here's the y momentum equation: u dv dx, v dv dy, dp dy, two second derivatives. So we're going to go ahead and put our scales in for that. So we have u infinity for u, we have delta over L u infinity for v, and then of course we have L. Second term, we have two v's in the numerator there. So we have delta over L u infinity, delta over L u infinity for both the v's, and then we have the y scale, which is the delta. Then we have 1 over rho p and delta, and then we have comma nu delta over L u infinity for that v scale, and then L squared, and then in the second term we have nu delta over L u infinity for that v again, and then this time over delta squared. Well, clearly, this term and this term, the numerators are the same magnitude, but one is divided by delta squared and one is divided by L squared. So just as we had with the X momentum equation, the one divided by delta squared is going to be hugely, hugely bigger than the one divided by L squared because delta is so much smaller than L. So this term is negligible compared to this term. So we can say that this term is going to be dominant, this term is going to be negligible because they're similar terms, but this one is much clearly, well, they're identical, except this one's clearly bigger. And so then this over here, these are going to come out to have the same scale again, but not as the X momentum, but they're going to be the same as each other. So we're going to have u infinity squared, and then this is delta over L squared for that one. And then for this one, we have u infinity squared again, and then delta over L squared again. So we have delta over L squared. So our scales, those are the same size as each other. So we have that one, we have this one, we still have P over delta, and we have nu, delta, I'm going to clean this up a little bit. So that's going to be nu, multiply up and down by L, so I get, and divide by 1 delta, so I get u infinity L delta. Yeah, that looks right. All right, so now we're going to combine these because these have the same size. So we have the three scales once again. We have the inertial scale, the pressure scale, and the viscous scale. So we have u infinity squared over L squared times delta for that inertial term. And then we have 1 over rho P over delta for the pressure term. Sorry, that's order of. And then we have nu u infinity over L delta for the viscous term. So those are our three terms.